Welcome, network engineers and architects. Today, we are focusing on a critical operational skill for AI data centers: how to monitor and tune network performance within NVIDIA Spectrum networking environments. Let's get started. Let's start by defining what performance monitoring means in an NVIDIA Spectrum network. It is the continuous, proactive analysis and tuning of your data center fabric. The basics represent a massive paradigm shift. We are moving away from traditional, slow SNMP polling and embracing real-time, ASIC-level streaming telemetry. Why is this mandatory today? Because AI workloads generate massive, synchronized bursts of data known as elephant flows. In an AI factory, if a microburst overflows a buffer and drops a packet, the entire GPU cluster halts to wait for retransmission. This drastically degrades your job completion time. How do we prevent this? By utilizing NVIDIA's advanced toolset, NVIDIA for localized switch data, what just happened for packet-level drop analysis, and NetQ for fabric-wide correlation. In our deep dive, it's crucial to understand that Spectrum switches process this telemetry in dedicated hardware, meaning you get extreme visibility with zero impact to your actual network traffic. Looking at this flowchart, you can see the architecture of Spectrum telemetry. The ASIC splits operations into two dedicated pipelines. While your heavy data plane traffic flows uninterrupted, the dedicated telemetry pipeline continuously streams data out to NVIDIA, the WGH engine, and the NetQ agent. This data is then aggregated into your centralized NetQ dashboard, providing a complete, non-blocking view of your network's health. Slide 2 focuses on localized visibility using NVIDIA, the NVIDIA user experience. What is it? NVIDIA is a fully schema-driven, object-oriented model that manages the entire Cumulus Linux switch. The basics involve using its CLI or REST API to extract real-time performance metrics. Why start here? Because before you can tune a network, you must establish a baseline and rule out layer 1 or layer 2 physical errors on your high-speed uplinks. How do we do this? Look at our sample code, NVShow interface SWP1 link stats. This simple command provides immediate visibility into inbound bytes, dropped packets, and carrier transitions. If carrier transitions is incrementing, you have a flapping physical link. For our deep dive, remember that NVIDIA isn't just a CLI. It provides this exact same structured data via a REST API in JSON format, making it incredibly powerful for automated monitoring scripts. This sequence diagram illustrates the flow of an NVIDIA telemetry request. When the administrator runs the show interface command, the NVIDIA engine translates this object query to the switch kernel. The kernel then fetches the live hardware counters directly from the Spectrum ASIC, formats the raw data, and returns it to the administrator as clean, structured CLI text or a JSON payload. Now we transition to one of the most powerful features in the Spectrum portfolio, what just happened, or WGH. What is it? It is a hardware-accelerated telemetry engine built right into the ASIC. The basics are simple but profound. Instead of looking at a generic counter that says 100 packets dropped, WGH tells you exactly which packets dropped and the precise reason why. Why is this revolutionary? In AI networks, troubleshooting a dropped packet across thousands of ports using traditional logs is like finding a needle in a haystack. WGH gives you the needle. How do you use it? You simply enable it in NVIDIA with NV set system WGH enable on. The deep dive here is that WGH captures the actual 5-tuple header of the dropped packet source IP, destination IP, ports, and protocol along with the drop reason, such as an ACL violation or a buffer tail drop, streaming this directly to your dashboard. Follow the path of a packet in this flowchart. It enters the switch and hits the ASIC. If everything is fine, it forwards normally. But if there is congestion or a configuration error, the packet is dropped. Instantly, the WGH engine intercepts the event, captures the packet header and the specific drop reason, and streams a JSON payload out to NetQ. The administrator immediately sees the root cause without touching a single log file. Slide 4 expands our view from a single switch to the entire data center fabric using NVIDIA NetQ. What is NetQ? It is a highly scalable, centralized observability platform. The basics involve lightweight agents running on every Cumulus Linux switch, which continuously stream telemetry back to the NetQ server. Why do we need this? Because when an AI workload spans hundreds of nodes, logging into individual switches to troubleshoot is impossible. You need correlated data. How NetQ solves this is through a rich graphical interface that aggregates all WGH events, link states, and BGP sessions into one view. The deep dive feature here is NetQ's time machine. NetQ records every state change. If an AI job failed at 2:00 a.m., you can rewind the NetQ dashboard to exactly 2:00 a.m. and view the precise routing tables, buffer occupancies, and link states as they existed at that very millisecond. This diagram shows the distributed architecture of NetQ. At the bottom, every leaf and spine switch runs a NetQ agent. These agents push streaming state data link changes, routing updates, WH drops up into the centralized NetQ telemetry database. The dashboard then processes this massive data pool to provide fabric-wide flow analysis and visualizations to the operations team. Once we have visibility, we must tune the network for performance, specifically for row-CER'd EMA over converged Ethernet. What is this? It's the mechanism that makes Ethernet act like a lossless fabric for AI. By default, Ethernet will drop packets when buffers fill up. In AI, this is catastrophic. Why? Because of incast congestion, where multiple GPUs send data to one destination simultaneously, creating microbursts. To tune this, we configure QoS using ECN, and PFC priority flow control prevents drops by pausing traffic, but it's a blunt instrument. Explicit congestion notification, or ECN, is our surgical tool. Look at the sample code. We enable ECN on traffic class 0. For our deep dive, understand that ECN is predictive. We tune buffer thresholds in NVIDIA. When the buffer hits a min threshold, the Spectrum switch flips a bit in the packet header. The receiving NIC sees this and tells the sender to slow down, gracefully avoiding congestion before a drop ever happens. Let's trace the ECN tuning flow. The sender GPU pushes data at a high rate into the Spectrum switch buffer. As the buffer crosses our tuned minimum threshold, the switch intelligently marks the ECN bit on the packet instead of dropping it. The receiver GPU gets the packet, sees the mark, and sends a notification back to the sender. The sender immediately throttles its transmission rate, safely clearing the congestion. Let's look at a highly critical real-time use case. Imagine you are monitoring a massive AI training run, and suddenly the data scientists report severe latency spikes. You check your legacy SNMP monitoring, and everything looks green. Average bandwidth is low, no ports are down. This is the danger of microbursts. They happen in microseconds, invisible to SNMP. So, you turn to NetQ and pull up what just happened. Immediately, WH flags buffer tail drops on leaf 02. The analysis shows the drops are specifically hitting your roast traffic on UDP port 4791. You have an incast microburst problem. To fix it, you take a tuning action, you log into NVIDIA and lower your ECN minimum threshold. This means the switch will start warning senders to slow down much earlier in the buffer lifecycle. The result, senders throttle back preemptively, the tail drops stop completely in WH, and the AI training job returns to peak performance. This sequence diagram maps our troubleshooting lifecycle. The AI job generates microbursts, causing the switch to experience tail drops. WH instantly catches this and alerts the admin. The admin responds by tuning the switch via NVIDIA, lowering the ECN threshold. The switch now sends early ECN marks, causing the AI job to throttle its bursts. Drops are eliminated and the system restores to a healthy state. On our final slide, we cover advanced hardware diagnostics. When you push configurations, you must ensure the hardware actually has the capacity to program them. By using the CL resource query command in Cumulus Linux, you can view the exact hardware utilization of your ASIC's TCM, routing tables, and ACL limits. This prevents silent failures where a route is learned but drops because the silicon is full. To summarize our session, effective Spectrum network operations require a holistic approach. You must monitor using NVIDIA and NetQ for streaming telemetry. You must diagnose utilizing the surgical precision of WH to find root causes. And you must tune your ROS, ECN, and PFC parameters to ensure a pristine, lossless environment. Mastering this guarantees your network will never bottleneck your expensive GPUs. I invite learners to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. This mind map serves as your operational cheat sheet. The core of Spectrum performance revolves around 3 pillars. First, monitor using NVIDIA and NetQ. Second, diagnose down to the hardware level using WH and resource queries. Third, tune your environment by optimizing ROS, PFC, and ECN. Commit this workflow to memory, and you will excel in AI networking.
Welcome to quicktechie.com. So just type in quicktechie.com here. Then you can go through the material which is provided by quicktechie. So we have first of all video courses which you can go here and you can find the various video courses across the technologies as well as finance domain. So if you see in Microsoft, we have 8 programs currently running. Next, you can go through the ebooks available. So all the ebooks which are in PDF format today, and you can download this. So let me go through Microsoft certification ebooks. You can click on any of this and you can see this is the PDF available for you to download. So these are the premium ebook mostly available on quicktechie.com platform only. Now the second part is exam simulator. As we primarily focus on the all technology companies and finance domain certification preparation material, so this is company wide listed here and you can go through this. So let me go through the Microsoft one again. You can see these are all Microsoft related certification. AB 730 exam, if you open it, so you can see here this, and all the practice papers are available here. Today we have a 5 practice paper. So click on the first practice paper, it would load the questions. You can answer this question. This is way you can answer it and you can move to the next question. Now the third material we wanted to highlight is an audiobook. So we started recently with the audiobooks as well, which you can listen on the go, and various technology wise ebooks are available. And at the last, this is our alumni. These people who are subscribing to our courses and this platform, they are all listed here. And at the end, I wanted to tell you, if you find any course or training or certification preparation material which you want to get us prepare for yourself, please put on the comment section. If you're watching on YouTube, on Udemy, or on this platform itself, quicktechie.com, then please put the comment, or you can even send an email to using this contact us options here. You can directly do the WhatsApp message. You can call us on this numbers as well.